Welcome. Today we are mastering the washer method, a powerful calculus technique for finding the volume of a solid of revolution. We use this specifically when the region being rotated does not touch the axis of revolution, creating a hollow center or a hole. By the end of this video, you will be able to handle complex rotations around shifted horizontal axes using horizontal slices. When our boundaries are defined as functions of y, or when we rotate around a horizontal axis and want to use the washer method, horizontal slices are often our best friend. This requires us to set up our integral in terms of y, looking at the thickness of our slices as a dy rather than a dx. This shift in perspective is crucial for solving problems involving horizontal rotation. Before we dive in, ensure you are comfortable with basic integration and the disk method. Remember, a washer is simply a large disk with a smaller disk removed from its center. If you can calculate the area of a circle, you are already halfway to understanding the geometry of the washer method. We are just stacking these areas along an axis. The general formula for the volume using the washer method is the integral of the cross-sectional area. This area is pi times the outer radius squared minus the inner radius squared. We integrate this expression from our lower y limit to our upper y limit. This effectively sums up an infinite number of infinitely thin washers to find the total volume. Looking at our specific region, the curve furthest from our axis y equals -1 is the line x equals 2y at the top of the region, and the closer curve is the parabola x equals y squared. Therefore, the outer radius r of y is the upper function minus the axis, and the inner radius r is the lower function minus the axis. Now we set up our integral. The volume v equals pi times the integral from 0 to 2 of the quantity 2y plus 1 squared, minus the quantity y squared plus 1 squared, with respect to y. That plus 1 comes from subtracting the -1 axis. This adjustment is the most critical step in handling shifted axes correctly. Before integrating, we must expand the squares. 2y plus 1 squared becomes 4y squared plus 4y plus 1. Y squared plus 1 squared becomes y to the fourth plus 2y squared plus 1. When we subtract the second from the first, the constants cancel out, leaving us with -y to the fourth plus 2y squared plus 4y. Now we apply the power rule for integration. The integral of -y to the fourth is -y to the fifth over 5. The integral of 2y squared is 2/3 y cubed, and the integral of 4y is 2y squared. We will evaluate this entire expression from our lower bound of 0 to our upper bound of 2. Plugging in 2, we get -32/5 plus 16/3 plus 8. Using a common denominator of 15, this simplifies to -96 plus 80 plus 120, all over 15. The final volume is 104 pi over 15 cubic units. This represents the total space occupied by our rotated solid. What if the axis is above the region? Let's rotate the area bounded by y equals x squared and y equals for around the axis y equals 5. Even though the axis is higher, the logic remains the same. The radius is always the distance between the curve and the axis of rotation. Since we are rotating around a horizontal axis and want to practice horizontal slices, we convert our function. Y equals x squared becomes x equals the square root of y for the right half. Note that horizontal slices here would actually be more complex than vertical ones, but we use them to illustrate the coordinate consistency required for y integration. The distance between a point at height y and the axis at y equals 5 is the absolute difference, 5 minus y. When we square this distance in our formula, the order doesn't matter, but it's good practice to think of it as top minus bottoms to keep the value positive and intuitive. In this scenario, the inner radius cart is the distance from the axis to the closest part of the region, and the outer radius art is the distance to the furthest part. Visualizing this gap is key to ensuring you don't accidentally calculate the volume of this hole instead of the solid. Sometimes the curves aren't simple polynomials. If we have x equals natural log of y and x equals e to the y, the process is identical. Identify the axis, determine which curve is further at a given y interval, and subtract the axis value from the function value to find your radii. Wait, let's clarify an important distinction. If we rotate around a horizontal axis using horizontal slices, we are actually describing the shell method. For the washer method around a horizontal axis, we typically use vertical slices, dx. If you are forced to use horizontal slices, dy, for a horizontal axis, you are doing the shell method. Let's pivot to ensure we are using the washer method correctly. To use the washer method on a horizontal axis like y equals -1, we must use vertical slices, which means integrating with respect to x. This ensures our slices are perpendicular to the axis of rotation, creating the characteristic washer shape. Let's re-examine our first example with this correct pairing. Using vertical slices for our horizontal axis y equals -1, we look at the height. The top curve is y equals square root of x and the bottom is y equals x over 2. The outer radius r of x is the top curve minus the axis, and the inner radius r is the bottom curve minus the axis. A very common mistake is to subtract the functions first and then square the result. This is incorrect. You must square the outer radius and the inner radius separately before subtracting. Mathematically, the area of a ring is pi r squared minus pi r squared, which factors to pi times the difference of the squares. To summarize the washer method, first, sketch your region and the axis of revolution. Second, identify your outer and inner radii by measuring the distance from the curves to the axis. Third, set up your integral using the difference of squares. Finally, determine your limits of integration based on where the curves intersect. Here is a quick challenge for you. If we rotate the region bounded by y equals x, the x-axis, and x equals 2 around the line y equals -2, what is the expression for the outer radius r of x? Think about the distance from the furthest curve to the axis. The correct answer is x plus 2. The curve furthest from the axis y equals -2 is the line y equals x. The distance between them is x minus -2, which simplifies to x plus 2. The inner radius would be the distance from the x-axis, y equals 0, to the axis, which is a constant 2. The washer method is an essential tool for volume problems with internal voids. By carefully defining your radii relative to the axis of rotation and ensuring your slices are perpendicular to that axis, you can solve even the most complex shifted axis problems. Mastery comes with practicing the setup and being meticulous with your algebra. Thank you for joining this lesson on the washer method. With these steps, you are ready to tackle any solid of revolution involving shifted horizontal axes. Keep practicing your sketches and integration. Generated by Vision Solve AI.